Okay, so what do you mean by orthogonal, right? We say that, just give me a second. I hope there are no. Okay. We say that the two vectors v w belonging to v are orthogonal. So when do you say that the two vectors are orthogonal? If, yeah, so when you take the dot product of two vectors, if it is 0, they are orthogonal, right? Perpendicular. So how do I generalize this? You take inner product of these two vectors, it should be 0, right? Then we say that the two vectors are orthogonal. When do you say that it's orthonormal? We say that, and I'll continue here. Okay, so and orthonormal if, what are the conditions? First of all, it has to be orthogonal, obviously, is 0. And what is the second thing? Normal means what? I mean, it should have unit length, right? So the norm of V should be equal to 1. Okay. So typically this norm is induced by the inner product. Okay. So you should not use completely different norm for normalizing and inner product. Okay. So is this fine? There are several examples, right? So what is an orthonormal basis in R3? Easy, right? 1, 0, 0, 0, 1, 0, and then 0, 0, 1 basis. Are there any other example of orthonormal basis in here? What is that? Okay, so you have to think about it, right? So something like, maybe I'll give, let me make my life easier. So in R2, let's see. I have, for example, 1 by root 2, 1 by root 2. If you look at Euclidean norm, this has norm 1. Okay. Now, I want to come up with the basis. This is one vector, right? What will be the other vector? Minus 1 by root 2. So these two vectors form an orthonormal basis. Okay, so in other words, if the basis turned out to be orthonormal, then we call that as an orthonormal basis, right? Okay. Now the other thing is, if you are dealing with orthonormal basis, it's very easy. Okay, so things are nice because I can take the inner product of the two different bases will be 0 and all that. Okay, so it's very simple and straightforward. Therefore, given a set of vectors, I should always be able to come up with orthonormal vectors. Now the question is, how do you do that? For example, let's say I have these two vectors, okay, or maybe these two vectors will form a basis. Do you agree? Huh? So I'll call this as v1 and this is v2. These form a basis, right? Do you agree with this? R2. That means you give me any vector in R2, I can write it as linear. Very intuitive. But are these orthonormal? First of all, it's not normal. It will have different lengths. Secondly, it's not orthogonal, right? They are not perpendicular to each other. But can we come up with the orthonormal basis using this? So what is the procedure? Well, pictorially, I can say, I'll draw a perpendicular here and do it. Well, two-dimensional, yeah, you can manage. Three-dimensional also you can somehow manage if you have good imagination. But fourth dimensional is hopeless, right? So you don't know how to do that, right? So what do? First of all, the first step is I'll normalize this, okay? To make it a unit vector, what do? Let's say I do v1 over norm of v1, okay? So in other words, think of it as a Euclidean norm, right? Square of the sum root. So this gives me a unit vector along the direction v1, okay? Is that fine? So I call it as u1. So u1 is a normal vector along the direction of v1. Now I have to come up with another vector which is orthogonal to this. How do you come up with the orthogonal vector? Suppose by some means, let's say, I could get this. What is this? How do you find this? Huh? Projection, right? So what is projection? Well, I haven't taught you what projection is, right? So what is a projection? Huh? So essentially, I have to take, so if I want to project V onto U, it's V transpose U, right? In Euclidean space, right? So this is nothing but, the length of this is nothing but V2 transpose U1. I'm going to project onto U1, unit vector, not V1, okay? So I'll project it onto this, okay? Now, I have to come up with a vector that is orthogonal. How do you find the orthogonal vector now? Now, you look at this vector, no? So, this vector is orthogonal, right? So, what is this vector? Let me write it here. What is this vector? This vector minus this vector, right? That will give me the orthogonal vector. What is that? What is this vector? I have to move by a distance along the direction of u1. I have to move by this distance, right? What is this distance? This distance is given by the inner product, right? u2 transpose v2 transpose u1, right? But along the direction of u1. So let me write it, or I'll do one thing. So this vector, I'm sorry, it's very clumsy, but this vector is what? I have to go in the direction of u1, so it will be u1. But how much? v2 transpose u1 distance I have to go, right? This will be the vector. So what is the orthogonal vector? It's this minus, so v2 transpose u1 times u1 minus v2, right? Right? So now this is the vector that we get, but is it orthogonal to u1? Is it orthogonal to u1? So how do you find that? How do you find that? You have to take the inner product and see, right? So, or dot product in this case and see. So how do you find that? u1 transpose times this will give me the answer, right? So what is u1 transpose u1 minus u1 transpose v2, right? That's what we get. You agree? So how do you, is this correct? Did I make any mistake? Yeah, so this is u1 along the direction of u1. Yeah, this is okay. So now u1 transpose times, I have to see this whether this is orthogonal or not, right? u1 minus v2. So what do we get now? What do we get? So u1 transpose u1 is what? 1, because it's a unit vector, right? So the first term will be v2 transpose u1 minus u1 transpose v2, but u1 transpose v2 is same as v2 transpose u1, so this is 0. So it's orthogonal, right? This is correct. So I get an orthogonal vector. Is that done? I got orthogonal basis now. It's orthogonal, but is it orthonormal? No. What do I do? Divide it by norm, right? So all that I have to do is, if I call this as u2, right? Let me call this as u2 dash. Okay. What should I do? u2 dash divided by norm of u2 dash is u2. I'll call u2 as u2 dash divided by norm of u2 dash. This gives me normalized. So u1 and u2 will give me orthonormal vectors, right? So what is this process called? Any idea? What is this process called? Simple geometry, right? High school, right? So what is this process called? This process is called Gram-Schmidt's orthogonalization procedure, right? Heard of it or no? No? Hey, linear algebra, if you had taken linear algebra, most likely you would have, in math you haven't studied linear algebra, you haven't studied Gram-Schmidt's? Yes or no? At least you tell me. Yes. Huh. This is what, right? But you should know this, right? So is this strange? Okay. So by the way, you can apply the same thing for your functions also. If I give, let's say, f1 through fn, n functions in the function space, right? I can think of it as a vector space with an inner product and so on. You can use exactly the same procedure to get n orthonormal functions. Okay. That leads to Fourier and all that. Anyway. Okay. So let's generalize this. What should we? How do we generalize this? Wherever I divided by the norm, I'll divide it by the general norm. Wherever I did the dot product, I'll do the inner product. Okay. So let's look at the process. So this is Gram-Schmidt's. I hope the spelling is correct. Yeah. So what should I do first? Let's say the first thing is given, let's say, n vectors. Okay, v1, v2, etc., vn. So in earlier case, we were given only two vectors, v1, v2 in two dimension. This could be in any dimension. In fact, any vector space with an inner product. Okay. So what is the first thing that I do? I get u1, right? u1 is v1 over norm of v1. Done. This gives me a unit vector along v1 direction, right? What do I do after this? I should find a vector orthogonal to u1. So what do I do? Let's look at this, right? I have u1, then I found this. I took inner product, scaled it, and subtracted from v2, and then normalized it, right? So how do I write that? So what is the first thing that I have to do? I have to take v2 inner product with u1 and go along the direction of u1, subtract v2, right? So we subtracted v2 from that. Yeah, so subtract v2, right? So this gives me what? u2 dash. Now what do? u2 is u2 dash divided by norm of u2 dash. You can check that these are orthogonal and orthonormal. Okay. So what is the third step? See, now things will change, right? You have two vectors, and I have to, so u1 and u2 are two vectors which are orthonormal. Now I have to come up with the third vector which is orthogonal to both, right? So how do you do that? What do you do? What is it that you will do? Huh? What do you do? If you have third vector like this, and I have to project onto v1 and v2, right? I have to project, so how do you do that? So how do you project onto a plane, right? Or I can write it in terms of geometry. So it's like this, right? You have these two. This is, let's say, orthogonal, and you have a vector like this, which is not orthogonal. It's like this. So how do you project? What do you mean by projection? So let's do this. Okay. So I project it onto some point here. So what is this point? This point is a linear combination of u1 and u2, right? Do you agree? Let me call this as alpha 1 u1 plus alpha 2 u2. Okay. This is a point. And when I project, what do you mean by projection? So this should be orthogonal, right? Do you agree? That means this vector should be orthogonal to this vector, right? So how do you ensure that this is orthogonal to this, right? Let's try to do that. Let's take the projection of let's say alpha 1 u1, alpha 2 u2. I'm going to project, right? So if I project onto that, right? So the projection itself will give me this, right? So you agree? So now I want to ensure that this is orthogonal. How do I ensure? What do I do? So basically I have to project, right? That's the idea. Okay. So what I'm going to do now is we'll come back to this, right? How do you do projection? So let's say, intuitively, you know what projection is, right? You would have done that in your graphics and so on. So I'll use a symbol called proj, okay, which will project.